Thanks a lot, Yair, and thanks to all of you for coming to listen and for NUS for inviting me to come and talk here. I don't always do this, but I'll start with a disclaimer, right? That what I'm hoping to do here is lay out sort of the landscape of a field. It's a field that I'm involved with, so of course I'm here. You invited me, so I will tell you a little bit about my own work, but I want to emphasize that what's interesting about this topic is not really what I'm working on, but what the field is about and what the different questions are, and I hope to sort of give you a spread of all the interesting questions people are looking at, including many, many people who are not me. So, and in that respect, I will try to cover a sampling of some of what I think are the most fascinating questions and how they intersect with larger issues of philosophy, society, and many, many more things. But I will necessarily, just by virtue of time, have to omit certain things, and so this is just an encouragement to sort of, if you like what you hear, go and read more about it, and that's what I'll say first. So we're here today because of this, which is basically what I like to call, all you need to know about machine learning in one slide. And to use the language of Silicon Valley, what we've done is we've disrupted decision making with AI, right? And this disruption has been very fruitful. The reason I'm here today is because I guess, among other things, we are seeing the advent of automated decision making, broadly speaking, into all aspects of our life, and not just recommending which movie you watch or what music you hear, but in much more fundamentally sort of critical and profound ways. My examples for now will be very US-centric, and I apologize for that. But I think some of the issues are broad as well, and they sort of apply across the board in other areas. So apart from all the usual places where you think of an algorithm as sort of making decisions for you, whether it's a Google search or an Amazon recommendation, we are beginning to see, or we have been seeing, the use of decision making in places where they materially affect your life, right? So for example, among the things, I don't know if this happens in NUS, but at the University of Utah, possibly at Stanford and many other places that I've been involved with, universities are using data about applicants to build profiles of who should be admitted to college, what kind of cohort should be admitted, what are people likely to survive the first year, are people likely to make it through 4 years, are they going to spend too many years and cost a lot of money to the university. The universities are building profiles to make predictions about this, figure out what features are relevant for this, whether, I don't know, your verbal GRE score is important to success in grad school and things like that. So that's one aspect of, a very important aspect of your life, where you go to college, and that's being affected by automated systems. Another system, and again, this is probably, it's not news that we have systems that profile us to decide whether a good credit is for loans. What's new and newer, I guess, is that there's much more micro-targeting of your activity, including things like your social media and other aspects, especially if you're a small business, to figure out whether you should be given a loan. So if you're a small business in the US, you might go to a bank for a loan. They will outsource the decision of whether you should get a loan to some third party, like one of these. That will actually go trawl through your Yelp profile, your Facebook profile, your Instagram, whatever else you might have available, among other things, and use it to build some story of whether you're a good credit risk or not. In hiring, there is a number of companies now that will basically provide analytics for employers wishing to hire you. So for example, at the very basic level, they might scan your resume and say, oh my God, you use Comic Sans, we never want to hire you ever again. Or use Papyrus, which is awesome, and you should, no, I'm just kidding. So, or they'll make you run through a video interview on Skype. There may be another person at the end of the line or not, and they'll analyze, the way you do the interview to figure out what kind of personality profiles you are exhibiting. If this is scary, it should be. Just a disclaimer, one of the companies here is HireVue, is a company that I'm on the scientific advisory board for, so I just want to put that disclaimer out there. But there are many companies that are in this space looking at these kinds of things. Moving sort of beyond sort of the personal to the sort of, I guess, the national, there's lots of issues that come up in sort of national security. And again, this is very US-centric. The Customs and Border Patrol, I hope I can get back into the US after this talk. They want to build profiles to decide who will be a good immigrant, who will be a good person to sort of bring in. And again, a lot of countries have these scoring systems to decide who to allow to immigrate to their country. The CBP was talking about using, again, things like social media and other kinds of more ML-ish features to predict whether someone will be a valuable asset to society. The TSA for many years, rumored first and then more recently revealed by the ACLU, has this no-fly list where they would basically build predictive models. Even if you hadn't committed a crime, you might be put in a no-fly list based on associations and other factors. The US military is looking into the use of AI in sort of targeting systems for weapons, especially automated systems like drones. And again, they want to use AI broadly conceived to do this for them. And one of the most sort of pernicious areas, pernicious because of the consequences and because of the widespread use of it, is in the US, at least in the area of criminal justice. And I'll say a little bit more about this later on, where algorithms are being used to decide where police should patrol, who should be picked up for arrest, whether you should be given bail, what kind of sentence you should be given, and whether you should be released on parole at every step of the way. And this is an ongoing process across the country now, not just a hypothetical. These things are going on, okay? And lest you think that you're here and you're safe from all this craziness in the US, of course we all know about this. And I won't say, you know, we still don't have enough useful information on what's really going on, but in a couple of months I hope to. There's some new papers that are coming out on this. And maybe there'll be more to say about what's going on with the Chinese social credit system. So there are many, in the past when I used to talk about these, I would give people sort of case studies of issues where when you replace human by automated decision making, interesting and sometimes sort of dangerous things tend to happen. At this point, there are no longer articles about this, there are books about this, so I encourage you to go read the whole plethora of books that sort of talk about the ramifications of living in an algorithm-driven society. Some of them are quite nice, actually, I won't say more about that now. Nevertheless, the challenge, what we're beginning to see, though, as a research problem is that when you sort of introduce automated decision-making into society, broadly sort of conceived, there are a number of things that change or break or fall apart or just are not well suited for this kind of systems. And the challenge is to understand in what way automated decision making is better, when is it worse, or under what conditions can you do a better job of decision making using the data that we have available to us, and how to think about this entire space. And that's what I'm going to be talking to you about now. And one way to understand this question, especially coming from a computer science background, as computer scientists, we think of machine learning again as a tiny little box. Input comes in, you work very, very hard on building the box, and out comes a decision. And if you've been trained as a good data scientist, you don't think too much about where the input came from and where the outputs go. You're spending a lot of time building your system. You're training your ConvNet, or you're training your SVM. Maybe no one trains in SVM anymore, I don't know. So, because you're all building ConvNets. At any rate, you're not really thinking too much about the larger context. But to understand the role of decision-making systems of this kind in society, you do have to expand out. And so this talk, in a sense, will be about these expanding rings of context. Right? What happens when you start asking questions not just about the narrow aspects of building a model, but of what happens before and after and further beyond. And at some point, we'll realize that we're actually touching larger, deep questions about how we want to construct society, how society is constructed, and how our automated systems are affecting that construction. So this talk will go from the technical to the more abstract as we go along. And again, I'm happy to sort of take interruptions, take questions whenever you feel like the muse strikes you. Okay? All right. So let's start with sort of the first expansion of context, right? So the idea of this very controversial in some ways idea of fairness or unfairness. And what I mean by this is trying to understand, once we build a system that makes some kind of decision, here stylized as a simple binary classification, yes, no decision, is that decision fair or unbiased or non-discriminatory, and what these words even mean. Okay. Now, of course, you know, we are, well, I'm a computer scientist, and if someone's telling me, oh, I want to study fairness, I'll say, okay, good, what's your definition of fairness? In some ways, that may be the wrong question to ask, but in some ways, it's a question, if you don't answer, you can't go any further forward. So well, let's start with that. Okay? So let's sort of give some context for where these definitions of fairness or unfairness might come from, and how we work with them and how we think about them. And to do this, we'll take a very simple problem, the simple problem of binary classification, not because everything in life is binary classification, but many things are, and it's a good approximation for how we want to think about this. So there are many, many more general questions where the setting of binary classification is not well suited, but even just thinking about this problem helps us understand where our notions, our normative notions of fairness are coming from. Right? And so, for example, you might decide whether you want to hire someone or not, you want to admit them to college or not, you want to give them a loan or not. How would you approach this question of fairness? So what I'm going to do now is give you sort of a brief sort of review of how in the last 10 years or so, we in the sort of this area of fairness, accountability, transparency have been thinking about this, but then I want to connect this to a much larger discussion that's been going on, depending on who you ask, for almost 2,000 years about ideas of justice and fairness. So let's start with some basic definitions. So on the left side, you'll see sort of problems. On the right side, you'll see, to be very glib about it, solutions. And so let's think of the top sort of two clouds right now. So suppose you have a situation where people are being treated differently, say based on their race. Again, some of this is going to be very US-centric. Race is, of course, a big issue in how we think about justice and fairness in the US, and that may not be true. And I think I encourage you to think about or share, a context that might be more relevant in the context here, right? So one way to think about, if you have to think about, okay, what might be wrong about this, is some sensibility that maybe for the particular task that you're trying to treat people for, their race is not a relevant factor. This is some belief that you have. And in particular, what you would like to articulate is a different belief, that you treat people with similar abilities for a task, where here you're implicitly saying, I don't think race is a relevant ability for your task, but whatever abilities you do have, if two people are similar, they should be treated similarly. If they are equally incompetent, they should both not be hired. If they're equally competent, they should both have an equal chance of being hired for the job. Right? And so there's a very sort of it's what is in the literature, at least people have called an individual fairness notion, because it rests on the idea of looking at two individuals alone. Right? People are similar. And of course, I mean, I'm not claiming that this is a formal definition. We'll get to attempts to make it formal in a bit. But this is how the sensibility you want. People who are similar should be treated similarly. A different notion that people have sort of called group fairness in different contexts says, what we're trying to worry about here is not treatment or equal treatment on the level of individuals, but equal treatment at the level of groups. In other words, we're worried about potential for structural bias against groups. Maybe minorities have been historically mistreated in a certain area, and you're worried about that, right? And so then you frame the question not at the individual level of individuals should be treated similarly. You frame the question at the group level of group should be treated similarly. And again, there are lots of questions about what that actually means, but that's again the sensibility. And so if you're all like fired up and ready to go, this whole fairness area is hot, you want to build a fair machine learning system, you kind of get stuck here because you say, okay, now I need to translate this into something a bit more precise that I can actually work with. And so one of the things that people have done is try to sort of come up with a more formalization of these notions. So for example, one way you could formalize the notion of individual fairness that people have done is to say, I have some notion of similarity between individuals, which I capture by some distance function d. That's on the left side. And assuming that if I'm given that distance function, this is a big assumption, but assuming I'm given such a distance function, then I want their outcome measured by the other distance function. So the c is the classifier. And so I want to look at the difference between their outcomes, and I want that to be small as well. So if they're close in the input, they should be close in the output, where close might mean different things depending on which metric space you're in. Okay? Again, I'm not saying this is the only way to do this, but this is one way you could try to capture this. And this, of course, is from sort of one of the early papers on this area by Dwork et al. This is from 2012. That's sort of formally this idea here. Similarly, if you wish to capture a notion of group fairness, you need introduce some more notation. Let's say there's a group variable, and the group variable has two values. It has 0 or 1. Right? So let's say 0 refers to the minority group in this case, the discriminated against group, and 1 refers to the majority group, the group that you you perceive as having had the benefit in the past. Then what you want to say is that the conditional probability of an outcome for each group should be more or less the same. This is one way of thinking about this. What is called sort of the statistical discrepancy or statistical demographic parity argument, saying that the behavior of your system on the two groups should look the same. If you hire 10% of one group, you should hire 10% of the other group. And you may not be able to do this exactly. It might be approximate. So you can say, well, the difference in these two things should be small, or the ratio should be not too far away from 1. There are different ways you could formulate this question. Right? The second one actually has legal relevance in the US as well. Now, of course, again, you're not limited to these. There are other ways you could try to capture some notion of fairness. Another way that people have thought about is what is often called an equal opportunity notion. And what I mean by that is that you're not trying to now equalize the outcome for groups, because maybe it turns out that there are one group is in fact maybe better qualified for the task at hand than the other, and you don't want to sort of bias that base fact with your measure. But you might say, I don't want to have, if I'm going to make mistakes in my classification, if I'm going to have a bad classifier, I want it to spread the errors out uniformly across the groups. I don't want to have one group be systematically given mistreatment versus another. There's a larger context for, so in this particular case, we're saying the false positive, false negative vector for one group should look more or less like the false positive, false negative vector for another group. And of course, you could generalize this in many ways. You can look at the 2x2 contingency matrix. You could look at different ways of doing predicted versus truth, and you could equate these two in some form. The historical, sort of one reason why this notion sort of came up, at least in the recent context, is because of this sort of famous case that a news organization called ProPublica brought out, where it turned out that a system that was releasing inmates on parole in Florida was trying to release inmates at roughly the same rate based on race, but was more likely to keep minority inmates in jail and not release them erroneously. And the erroneously part is sort of interesting to test because they actually had to go and track down inmates after they were released and see what they did and so on. So this motivation comes from there. And of course, there are other ways to capture this. There was a tutorial last year at the FATSTAR conference that had a sort of description of 21 different notions of fairness. But there's been also a lot of interesting work on trying to sort of unify these different notions together. I should point out that these notions are not the same. There are theoretical results sort of proving that they are essentially incompatible. It means trying to optimize for one measure will force you to not optimize for another measure. So they're not, in some sense, reducible to each other. They're distinguishable. So, but again, like I said, there are many unifying notions of fairness. There was some work that sort of said, okay, look, what you're generally saying is that you want some outcome. You want the outcome to be independent of the group, but you might have some other conditioning under which you want it to be independent. So it's a conditional independence and not a sort of full independence. And then they showed that you can capture many of the notions we talked about in this sort of general framework by choosing your outcome and the thing you're conditioning on in various ways, right? Another sort of body of work said, okay, look, I want to be able to optimize these, I want to be able to learn with these different fairness measures, and I'll get to that in a bit. So I want to have a way of coming up with an optimization function that I can sort of chug through my solver. And so I can generalize this in, again, some form. So linear combinations of conditional outcomes independent of group. Again, this generalizes all these different notions. So this, and furthermore, so a more recent paper sort of said, okay, let's think about this not in the context of group characteristics or what race you are or what gender you are, but let's think of this in terms of circumstantial features that you cannot control versus features you can control. So this borrows from the literature on equality of opportunity from economics, especially due to sort of Romer. And there you say you want the outcome to be independent of your circumstantial features, but should relate to your effort. If you don't put enough effort, you shouldn't get a good outcome. But if for two people who put in the same amount of effort, then the outcome should be independent of what other uncontrollable features you have. And so assuming you can specify these things in your system, then you can formulate it. And again, the whole point was that you could capture standard notions of bias in these larger frameworks here. And from a more sort of theoretical perspective, another direction which is sort of interesting is to not take this, what I'll call information theoretic view on these problems, but a more computational view. And so there's a bunch of papers that basically said the following. So think of a group, right, as just something you define via a circuit. So you have some kind of Boolean predicate or some kind that defines what a group is, right? And it's a small circuit, it's a simple predicate to express. And now what you want to do is you want to make sure that you're not biased with respect to any such circuit, not just one. And again, the motivation here say, well, maybe I don't discriminate based on race. Maybe I don't discriminate based on gender. But maybe I'm discriminating against black women, for example, which is, again, the case study coming from a paper that got a lot of traction last year, where these researchers showed that these face recognition systems from Microsoft and IBM were specifically not trained well to sort of recognize the faces of dark-skinned women because of the way the systems were built. So this idea of intersectionality that comes up in sociology is what's relevant here. And so these are sort of computational approaches that were designed to sort of think through in a more formal way, what does it mean to be a group? And then how do you protect against any possible groups that are succinctly defined? And there's some nice theory here connecting this to the ability to build such systems to the hardness of agnostic learning, which I won't go into here. What I'm trying to do is sort of give you kind of a broad landscape of the different collection of measures you might be able to pick from. And they all capture some different aesthetic about, or some different set of norms of what we believe is important when we think about ensuring fairness or lack of unfairness in society. And I'll say a little bit more about the history of these notions later on. But if you do have such notions, right, what can you do with them? And so I want to make a little detour into how people have actually tried to build systems that are fair or prevent unfairness using these definitions. Right? So that's sort of my brief, you can think of this kind of a brief sort of deep dive into the mechanics of these systems. So if you want to make an algorithmic decision-making system fair in this definition of fair, what people have tried to look at is where do we insert some corrective features to try and say something about the output of this individual process. Okay. So for example, you could modify the training data that you have. If your training data is sort of fundamentally skewed, so for example, again, you're building a model for predicting whether someone will commit a crime after being released on parole. Historically, sort of criminal justice in the US has been very racially biased. Training data that you get from the past is going to be biased. Any system you build is going to reproduce that bias, so you need to compensate for that somehow. That might be one way of doing it. Change the training data input you get. Another approach might be to modify the algorithms you build. So you embed some kind of fairness regularizer, if you wish, into your machine learning algorithm itself. And another approach might be to sort of modify the output labels that you get based on what you want. And if you look at the literature on these mechanisms, this is what people have been doing over the years, sort of trying to see where you can do things one way or one other way or another. And so what I want to do is give you a brief flavor of how you might go up approaching these problems for a couple of these different intervention models. So let's look at, for example, what it means to modify the input. Right? So there's been sort of a bunch of work on this, and to understand what we're trying to deal with here, let's look at this basic problem. So let's talk about two kinds of bias, so direct bias and indirect bias. So you have some data set again, you have some predicted attribute, you have some unpredicted attributes, right? These are the attributes you want. So your goal is to determine some outcome. And an example of direct discrimination would be if you are deciding the outcome based on attributes that you don't want to decide the outcome on. And if you do this directly, this would be in some sense an easy thing. This is what is called disparate treatment in US law. And it would be fairly easy to detect it because you would have signs like this. This is a historical sort of sign from the Smithsonian from the sort of segregation era. So this is, a very sort of concrete, horrific example of direct discrimination. Right? You are directly saying we don't want people this kind here. But a lot of bias that we're worried about is much more subtle. It's more indirect bias. You're building some classifier to make predictions. The classifier is using a bunch of variables, but the problem is that they correlate with the thing that you're worried about. Right? So there's no direct, obvious evidence of discrimination, but it's coming through the signal coming from the variables that you're concerned about. And probably one of the most famous example of this is what is called redlining. Again, so this is so back in the 30s, at least nominally speaking, banks were not allowed to discriminate against minorities. They had to give loans to people who asked them based on the merits. But banks did not want to give loans to minorities. And this was from Chicago. And since they couldn't explicitly say we won't give you a loan if you're black, what they said was because neighborhoods are segregated, they literally drew red lines around certain neighborhoods and marked off certain neighborhoods as places where they would not give loans to people applying for loans for houses. So this practice was at the time called redlining, and is an example of how the zip code, in this case, correlates with an attribute that you're not supposed to discriminate against. And so you're creating an indirect bias by doing this. Okay? And so when you have to deal with problems of bias and avoiding bias in these systems, these are the kinds of problems you have to deal with. So how do you deal with this problem? How do you deal with this issue of indirect bias, where variables might be correlated in ways you don't really know anything about? So this is one example of how you might do this. We'll call this an information theoretic example of this. Think of it this way. Suppose you are trying to figure out whether a feature that on the surface does not have, let me say this again. Suppose you have a feature that's protected, and you know it's not in your data set, but you have some other features that might be correlated with it. One way to figure out if there is a signal between the features that look fine and the one that you're worried about is to see if there's information flow between them. Another way of saying this is to say, can you predict the unknown feature, the race, the gender, or whatever, from the data set you have? Right? So, in other words, can you modify your data set so that the variables you do end up with do not give you the ability to predict the attribute you're concerned about? Because if you could do this, then you are satisfied that your data set no longer contains a signal about the attribute you are worried about, which means your classifier, which after all is just a signal extraction mechanism, will not be able to extract such a signal. That's the idea. So think of this as an information theoretic property. We're saying you're saying information theoretically you want to eliminate any possibility of deriving a signal that could cause your algorithm to be biased. Because you don't, let's say in this case, you don't have control over how the algorithm is being built. All you have control over is the data set itself. So this is sort of work that I'd done a few years ago. It's sort of one of my first sort of, I guess, work in this area where we were looking at how you do this. And so again, you have a data set, it contains an attribute X, which remember is a predictor attribute you don't want to make predictions based on. You strip it out, and you get some new attributes, and see if you can predict it back, right? And if your error is high, and for those of you who know information theory, this will bear some echoes of Fano's inequality. If your prediction error is high when trying to predict X, then X and Y have very little shared information. And this is again a situation you want to be in, where you cannot extract information about the predictor attribute X from your data. What's nice about this is that, and this is the reason why we did this, if you remember that measure I told you about earlier, this measure of group fairness, which is a ratio, which says make sure the conditional probabilities of success for the two groups are roughly the same in ratio. This actually relates to a sort of a doctrine in US employment law that called the 4/5 rule that basically says that if you're hiring people for a job and you hire, the probability of hiring, the conditional probability based on the candidate pool and who you hired, the conditional probability for hiring a woman is 10%, and for men is 50%. Then 10 over 50 is 1 over 5, which is much less than 4/5, which means that someone has a potential for lodging a complaint, a discrimination complaint. It doesn't mean that this complaint will be accepted, but they have the potential for filing a case about this. And what's interesting about this doctrine in US law, which is actually very important for algorithmic decision making, is that it doesn't focus on intent. It doesn't ask you to prove that someone was explicitly biased, but it asks to look at the outcome. Okay? And what's nice about this measure is that you can show that in the process I described to you, if you can show that you can predict the predicted attribute X from Y with probability epsilon, then you can show that the classifier has potential disparate impact in the notion I just described to you with some level G of epsilon, where G is some function. So this is a good way to sort of tell whether this is a good way to to establish whether there's bias in your prediction system coming from your data set. So how do you do this intuitively? So intuitively, it's not terribly hard to think about this, right? So if you think of, let's say your data set, let's say you have, again, the two groups, and you look at the distribution of the data with respect to the two groups. Let's pretend this is a one-dimensional thing. So if you look at the distribution of data with respect to group 1, that's in red, the group 2, that's in blue. Intuitively, if I just tell you the value I receive, which is a number along the x-axis, with some reasonable probability, I'll be able to tell whether it was red or blue. In fact, the further apart these distributions are, the easier it will be for me to do this. And the closer they are, the harder it will be to do this. And this, of course, is the basis of the idea. What you want to do is make sure your conditional distributions kind of merge together. Because at that point, then there's no more information left in the system to distinguish the groups apart. And of course, you can do this very willy-nilly. You can just destroy all your data and do this. And this is kind of a thing where you could achieve fairness in some sense by destroying your data set. You don't, of course, want to do that because there is hopefully something of merit in your data to work with. So you want to do this in a kind of minimally invasive way. So this involves actually sort of some technical details, at least in one dimensions, involving using the earthmover distance to formulate this idea of moving distributions together and finding a minimizer of essentially the one center under the earthmover distance. There are details that you can sort of work through, and then eventually you end up with something that looks like this, somewhere in the middle between. Okay? And the idea again is that you have explicitly tried to move your distributions together to mask the label, red or blue in this case. Now that's all well and good if you have very structured data or if you have some very systematic way of doing this. But this doesn't even work, for example, in higher dimensions. In higher dimensions, you can use a heuristic where you move it dimension by dimension, but to do it much higher, it takes a lot more work, and that's actually quite complicated. So another way you might think about doing this is that why should I have to figure out how to move things together? In the spirit of how we think about design processes nowadays in the age of deep learning, can we build a system to learn the right way to change the representation of my data so that I can do this? So there's a series of nice work. So this starts off with work by Zemel et al. From 2013, work by Edwards and Storkey in 2016, and of course a recent paper, which I'm going to talk about right here, by Medras et al. just came out, that said, rather than trying to explicitly move distributions together and do that in a messy way, can we just learn the right representation? So in this system, we have some data X, we have some classification task that you want to sort of send X to Y, and you want to learn some representation Z that is nice for your task. And what does nice mean? Nice means that, first of all, the representation should be a good representation of X. So you should be able to encode your X into Z and then decode it back into X without too much loss. So it's a faithful representation of your input. You should be able to do your classification the way you want to. So given Z, you should be able to classify well with high accuracy. But you also want to make sure that if an adversary tries to learn a protected attribute, in this case A, from the latent the representation you learn Z, it will not be able to do so. Okay? So again, the idea here is, can we learn a modified representation of the data so it's high fidelity, it can be used for classification, but it resists attack by someone trying to figure out what the protected attribute is. And again, you know, the trick is to set this up appropriately, set up a neural network appropriately, set up the cost functions appropriately. What they show is that you can capture many of the notions of fairness I described earlier by choosing the appropriate loss functions when you're doing your neural network optimization. So it's quite a nice paper that sort of looks at this. And I think the point is that there's this general theme of learning the right representation of the data that guarantees you can solve your problem, but you don't have, your adversary cannot detect any kind of signal about the protected attribute from it. Yeah. The way the decoder setup is, so this diagram is not particularly, okay, so X, you can think of X as containing A inside it. So the decoder has access to the true A along with Z, but the adversary doesn't. So this is a bit misleading, and I apologize for that, but that's the point here, yeah. So the decoder has a bit more information than the adversary has, and that's why it takes care of your problem there. Yeah, thanks, yeah.
What are some example applications where you can do this, but not be throwing away information that would be useful to the algorithm?
So it turns out, right, so, and I can tell you this even from our work, right, from our early work on this, there are a couple of these sort of standard data sets that people play with. One is sort of a German credit data set that looks at sort of the denial or acceptance of credit to people and with other demographic features. It turns out you can remove a lot of sort of race and gender related attributes without too much loss in your ability to classify. For some cases, you can't. So what's interesting is that for some kinds of data sets, you can show that as you start removing any kind of signal coming from the attribute you're concerned about, your accuracy starts degrading very rapidly. And in some sense, what that's saying to you is that data set is sort of, it's inextricably linked. These things are linked together in a way that you cannot take them out. For some data sets, you can. So I'm not saying that this can always be done or can always be done well. But I think what it tells you is that if you can't, there is something else going on. And it might be worth your while to look into your data set to see what's happening with it. That's what I would say. Yeah, this question back. Yep. That's right.
I thought the original definition was that the two should be similar. There is no
Ah, so, right. So you could frame the question of, give me a representation that works for any classification task, regardless of what it is. These papers are looking at a much more narrow question of, knowing what classification task I have, can I come up with a better representation? There is other work, and I'm going to talk about that here, but there is sort of attempts at other work that is sort of purely in the representation realm that comes up with the representation that is independent of any classification task you might do on it. Right. So you're right that the version I described earlier would be independent because it just completely conflates these things. And one can argue that that might require too much, and this is a bit more only doing as much as you need to do for that task. So I think there's an interesting question of when one is more appropriate than the other. Yeah. Good. Thanks. Any questions? All right. So what we saw is a collection of approaches, and there are others like this, based on modifying the training data you put into a system that you may not have control over yourself. And I think I found that people often have this kind of visceral, you're changing the training data, that seems somehow wrong, it's unscientific, you're including your biases into your data, and it may not be to your taste. So another way you might be able to think about trying to incorporate some notions of fairness into your system is by saying, okay, I don't want to touch the data, but I have control over the training process. I have control over the algorithm I'm using to train my model. Can I train it in a better way? Can I put in, say, a good regularizer? Okay, so this is the picture that I want to here. So here again, there are other ways you can think about this. There's been some approaches to sort of look at this question. So let's go back to our basic question. I have a classifier. You know, it has some parameters theta, and it takes some input x, outputs a y hat. And again, as usual, I want to minimize some loss function over the parameters of the model, right? And here again, let's say my goal is to minimize this sort of error rate across groups. So each term there is representing an error rate. It's measuring the probability of my prediction not agreeing with the true value. But the two different values are the two values for two groups, z equal to 1, z equal to 0 in this case. And I want these numbers to be close, right? The problem is I can write down an optimization function. I can put this constraint in, but this constraint it's not a convex constraint. Doesn't sort of help me actually. I won't be able to actually learn a classifier with this kind of constraint. So there's been a series of work that says, okay, can we replace this by a proxy loss function that actually does something that is easier to optimize? It may still not be convex, but it's easier to optimize than this one. And so there's this set of papers by Zafar et al. That said, okay, if we want to encode this notion that the error rate is independent of the group label, we can express it by saying we want to eliminate any correlation between the sensitive attribute and your signed distance to the decision boundary, because that's a way to sort of quantitatively measure error. And in particular, what they do is they construct this covariance function, which is again this covariance between the sensitive attribute, the z's, and this weird distance function to the boundary, which for different kinds of classification tasks might look different. And then they show that essentially this can be used to optimize a classifier that sort of has a fairness regularizer baked into it. So again, there's a couple of papers that do this, but that's the basic strategy. Come up with a proxy for your fairness constraint that you can actually optimize over, and then do that if you don't want to change your input data. So there's been a lot of work in this sort of general area of how do you build these fairness measures, how do you optimize for them for each measure, and for each classifier you can imagine the whole paper trying to sort of optimize the measure for the classifier and so on. So one relevant question that you might have is, okay, well, I have all these different measures, how do they really relate to each other, right? Are they really all that different? Is there any way to sort of think about them in terms of how effective they are? So one piece of work that we did that will be published sort of in the next at our conference is sort of looking exactly at this question, right? How do we compare different notions of fairness? And so this is a purely empirical study that we did, and it sort of generates some interesting results. It said, okay, let's look at these sort of many different notions of fairness that people are looking at. Let's look at how they work when you try to optimize different algorithms, different sort of tasks based on these notions of fairness, and let's see what kind of errors you get, and then let's plot them in this gigantic correlation chart. So this is a sort of a matrix of correlations where basically blue is the high correlation and positive correlation, and red is the high negative correlation. And what you start seeing essentially are these, even though there are different measures, these kind of chunkings that appear, that certain measures start behaving very similarly to each other. So even though it looks like there are many different ways to measure the bias in your decision-making process, there aren't really that many different ways. And I think one thing that's sort of interesting about this is that it sort of suggests that maybe we rethink more carefully how we think about these different notions of fairness and whether they really are as different as we think they are. What's more interesting, though, or equally interesting, is that you can look at how stable these algorithms are under different under different choices of parameters, different choices of how they're run and how they're trained, and different algorithms. If you look at this, so if you look at each plot here, what you're seeing is basically the x-axis represents one form of a bias score, and the y-axis represents some notion of accuracy. Right? So you want things to be highly accurate and no bias. Of course, different algorithms situate themselves in different places. But they all have different sort of ranges of behavior based on how you choose the parameters, how you represent the inputs, and so on. So this issue of stability of different methods is something that I think is not being sort of fully explored, which is worth exploring as we get this whole sort of constellation of methods for studying fairness here. So that was sort of in some sense, a brief digression to give you a flavor of how people are actually instrumenting these notions for defining fairness in machine learning. And there are many more of them. So there's some interesting new work that's coming out. So this idea of recourse, right? Rather than measuring the degree to which a decision system is unfair, can we measure how much effort it would take for a point to cross the boundary? Well, why is this relevant? So suppose you're denied credit. So under US law, you can ask for an explanation. So the system has to give you an explanation as to why you're denied credit. They might say, oh, well, your credit score was too low because you have too many credit cards. So that explanation is kind of interesting because it says, okay, if it says that my score was low because I had too many credit cards, it's also saying, well, if you reduce the number of credit cards you have, your score might go up. It gives you an avenue for recourse. This is actually quite relevant, especially in the context of the GDPR, which of course is an EU-related sort of directive describing how algorithmic decision, among other things, how algorithmic decision making will be deployed in the EU, but it's also being used as a model for legislation in the US and also in Asia and some parts of Asia. Because what it's saying is that, if you want to give someone an explanation, you have to give them an explanation that they can work with, that they can do something about to change the decision that is made about them. And so this idea of recourse is an alternate way of thinking about fairness, is saying basically, can I express the consequences of my decision in terms of how much effort it would take me to change myself? And again, no discussion of this topic can be complete without talking about sort of notions of causality. And so people have been looking at what is called counterfactual fairness. How would the algorithm have changed decisions if the sensitive attribute was flipped? If suddenly, my profile was sent in, but my gender was changed, would the algorithm have changed the output? If it does, and I can define a measure on this, then this might be a problem for the algorithm as well. So again, there are many, many notions that people are exploring based on different aesthetics about how we think about what is reasonable decision making in a system. Okay. But what I want to do next is now go a bit further out, right? So we've talked about defining notions of fairness or notions of bias and how to measure it, how to build a system that might try to alleviate some of it, and so on. But there's often more that you want to do with such a system. You might want to inspect how the system even works before you even worry about anything else. So someone comes up with this wonderful new deep learning system to make predictions about like basically whether your brain scan says you will develop Alzheimer's later in life. The doctor's not just going to say, okay, fine, this says with probability 67% that you're going to develop Alzheimer's. They want to know why. And so this larger question of why is it a system is doing what it's doing leads me to a sort of another expansion of context, this idea of audits. Right? And more formally, the question I'm going to pose here is this. Right? Given a black box function, again, you can think of this as inputs to model and the output, determine the influence each variable has on the outcome. Right? So I'm expressing this somewhat narrowly, but I'll generalize this a little bit in a second. So some of the questions you might want to ask is, right, how do you quantify this influence? How do you model this influence? How do you handle different ways that variables might interact together? And so there's been a lot of interesting work in this area, a lot of it done by Yarzvik, who's sort of sitting in the room here, who just introduced me, thinking about this question. And so some of the questions that people have looked at is, okay, I have this y equal to f of x, where x is this vector of features. One question you could ask is, to what extent does the feature influence the model? This is an interesting question because you might say, okay, is the model using something that it shouldn't be using? For example, if I build a deep learning model to predict a chemical reaction, let's say, and this is something work that we've done with our colleagues, and the system for some reason feels that the time of day of the experiment is an important feature during the outcome, this might make me suspicious that the model knows what it's doing. Maybe there's something skewed in my data that the time of day variable is being used in a way that it shouldn't be. But it gives me a clue as to whether the model is making sense or not. And that's an important thing. So if I can answer this question, the extent to which a feature influences the model, I may have a better understanding of what a model that otherwise might be very complex is doing. But you can make this more specific, right? You can say, to what extent does the feature influence the outcome for a particular point? Right? So in other words, if I am, for example, if I am being denied parole, I don't care what features influence the model in general. I want to know what features of my profile were affecting the model. And that's a slightly different question. The answer to the first question will not give me an answer to the second question. And so there's been, while I won't talk about this in this talk, there's been some very nice work on this that I encourage you to sort of look at as well. And again, like I said, especially in the context of the GDPR, which sort of says, at least implies that an individual has a right to some explanation for a decision that was made about them by an algorithm, you could imagine that this would be one form of a decision, explanation that is generated. And so you would need tools to be able to do this. Right? So this has nothing to do with bias or sort of inequities in society in general. It is about getting a better lens on what our system is doing, an automated system. And again, this is because the system is being used in a context where individuals have the right to demand some kind of explanation. Right? I don't need an explanation for my Netflix recommendation, but I would like an explanation for why I didn't get a job or something. So again, going back to the early question of how do you determine whether a model, whether features influence models, some of these early ideas go back to the sort of work of Bremen on random forests. And it's a very simple idea. It says, look, I have a function that is dependent on certain variables. What I will now do is perturb a particular feature in a certain way. So I have a feature x1. I will perturb it in some form to generate an x1 prime. I will now compute a y prime, and I'll look at the change. So think of this like a derivative with a random perturbation, right? And if once I measure the perturbation, this gives me a sense of to what extent the output is sensitive to my input, right? And there's been a long line of work on this, of papers that have looked at this basic idea here. And of course, the devil is in the details here. And the key detail here is how do you design this intervention distribution? And so depending on how you design the intervention distribution, whether you use some kind of permutation testing or whether you use ideas from like game theory, these things called Shapley values, there are different ways in which you might try to sabotage the input to determine sensitivity. For those of you in the theory world who've looked at sort of Fourier analysis on Boolean functions, this is a very similar idea. So it's the same idea in fact, but sort of in a different context here. It's the same kind of ideas percolate through. But again, like I said, there's a whole body of work here which is very interesting, but a way to put a twist on this, say, look, I don't actually know what the right sort of sample distribution is to perturb my variable under. Let me ask the question a different way, in a more computational way, if you wish. Let me twist this around, and this is work that we did to say, again, using the same ideas talked about before, the information content of a feature can be estimated by trying to predict it from the remaining features. So if you can modify your input so that the influence of such a feature is low because I can't predict it from everything else, then I can see the extent to which it affected the outcome. Because now when I build my classifier, I'll see the extent to which my accuracy drops. If my accuracy dropped a lot, then this feature, either directly or indirectly, was very important. And again, this is particularly relevant when you have things like indirect influence of features, where a feature may not directly show up in your data set, but it influences other features in your data set. And so one example of this that we did was we were looking at, again, working with some chemists and trying to understand whether a particular deep learning system was predicting the output of a reaction correctly. They didn't want to actually run the experiment, so they actually had a deep learning system trained to predict outcomes, and they wanted to understand whether it was doing the right thing. So we would generate these plots for them. We would say, okay, how does the accuracy drop as you go from left to right, as you remove more and more content from the feature? How does this accuracy measured on the y-axis drop? Each color represents one feature. There were some 273 features in the set. The feature that influenced the output the most is the one for which the accuracy dropped the most. So if you read from bottom to top on the right-hand side, in each of these, for these different classification mechanisms, you can read off which features are the most influential in deciding the outcome. So it's a way to get a readout from your model, which might be a black box model, as to which features are influential and how it works. Okay? So there's a lot more work, I think, that needs to be done in this whole area of trying to audit a model. That's why I call it auditing, right? So you're given a black box model, you want to probe. You had a question, 2 questions back there. Okay. Okay. Noise in the system, because the proxy we were using in this case to remove information was at some level a heuristic. It was not a perfect proxy. If you had a perfect system, it would do it. But this represents inefficiencies in our system itself. Ideally, yes, you're right. It should always go down. Mm-hmm. Yeah. Which one? Yeah, I don't know. That's true. I don't. That seems sort of weird. I have to go and look into that. That was not. Yeah. Because most of the ones, they kind of the little bumps, but they mostly go down. That one, that is a little. I don't know. No, I don't know. I have to check that and see. That is kind of a good point. Pardon me? Right. And so that's why I said in an ideal process that stripped out the influence of the feature, this would not happen. Because it doesn't quite, you would get fluctuation. Whether it would be that much, I'm not sure so much, but that's another sort of thing. But yeah. Okay. So like I said, this idea of auditing a black box model is by no means a solved problem. I think it's a very important problem. We don't really have good way. I think there's both a technical problem, how to do this. There's a sort of let's say a visualization problem, how to visualize the answers. There's an HCI problem, what kinds of questions people want to ask such a system about what it's doing. And there's a lot of open questions I think are very fascinating to look at that I think we should be all looking at some more. But let me turn to another example of sort of a framing that we don't really think about too much, this idea of feedback loops. Oh yeah, sure. Yeah. Yes. Yes. You cannot audit well because things are right. And I think I suspect that audit mechanisms are helpful for maybe looking at a few features that you really care about. I don't think they give you if you expect them to give you an entire sort of landscape of all the features you're working with, I don't think it will work very well. So I think it'd be nice to look at more cases of where people are using audits to sort of understand what they will. In the cases we were looking at, the chemists, they only had about 5 or 6 features they were really worried about. And so that it was easy to generate answers for them. If you had more things you cared about, I don't know how well that would work.
So just to make sure I understood this, so you remove a feature and then retrain it?
You don't remove it. You mask its effect, basically, by essentially replacing it by noise in a careful way. So the data set still looks like it has the features, but the signal in content of the feature is kind of gone.
But now you get a new model, right? You retrain it.
Yes. You train a new model, and you look at the accuracy of the new model.
So, but this new model that you got could be very different from the
No. So sorry. Let me rephrase. What you do is you modify the data set, right? You do this. You actually you modify your test data as well, and you run the model on your test data, and you look at the errors you get in the test data. So your model has been trained. Okay, the model is trained. It's fixed. You're right. You have to have a fixed model there. Then when you do the modification, you modify the test data, and then you run the model on the test data. So the model stays fixed.
So how do you define the noise?
So the way you define noise is by saying, if you recall what we were saying earlier in the earlier part of the talk, I was saying you want to essentially corrupt the data distribution in a sort of minimally invasive way so that you lose a signal, right? That's a high level. Effectively what's happening is I have my table of data, I have my feature, the one that I'm sort of contaminating. I'm essentially replacing it by modified values in a way that allows me to merge these distributions together. So I replace it by different values. So they're there, but they're just different values. And then I run the model over this modified data. That make sense? All right. Another thing you have to worry about when you build these models and you use them in a decision-making system is the problem of feedback. And I think probably the most sort of telling example of where this comes up is in this area of what is called predictive policing. So predictive policing is the following set of problems. And again, this is something that sort of police departments across the US are doing. You have historical data about crime in different neighborhoods. You want to build a predictive model to see where crime is going to happen the next day. Why? Because you want to allocate your resources efficiently. You have limited resources in terms of officers, in terms of patrol cars. You have a large area to cover. You don't want to waste your time in areas where you don't think anything's going to happen. You want to put them in places where something might happen. So you want to do this on a daily basis. Every day you might come up with a heat map. So this is the term that's popularly used, a heat map of where things might happen, and you want to send people there. Okay? So these are some of the companies that have sort of built software for these things. One of the big sort of 800-pound gorillas in this area is a company called Palantir that again has been helping sort of somewhat secretly various jurisdictions to build these kinds of profiling systems. Now again, predictive policing works in sort of two flavors. This is what I call the sort of location-based profiling. There's also individual-based profiling, where they profile people based on where they're likely to sort of be involved in crime in some way. I'm not talking about that here. That's even more complicated. In some very interesting work from 2016, sort of Christian Lum and William Isaac sort of were looking at what could go wrong with such systems. And I think intuitively it's very easy to explain what could go wrong. Imagine you built a system for doing predictive policing, and it said, okay, send police here and here, but not there. So you send police here and here, but not there. Either the police see crime there, you're happy, your system worked. They saw crime where you sent them. Or they don't see crime, in which case you're also happy because you sent the police and they detected crime. In some sense, either way, it looks like your model's working. And what's worse, if you don't send police somewhere else, unless someone actually calls 911, you won't see any evidence of crime there. And lest you think that this is not a realistic problem, there are a lot of places where people will not call the cops even if they see something going on, because sometimes calling the cops is a bigger hassle than just living with the problem that they have. So in other words, your model is generating a further attempt to sort of collect data, which is censored by the fact that your model is only sending you to certain places. So the data you're collecting is now contaminated by your model predictions in a way that could potentially lead to all kinds of weird feedback problems. And so intuitively, this kind of makes sense. This could happen. The question is whether it does happen. So what they did was this experiment where they got published descriptions of the code that one of these companies, Predpol, was using to do these predictions. They looked at an area of the East Bay in California, in the Bay Area. This is an area called Oakland, which is sort of historically has had sort of major issues with crime and policing. And they looked at, based on national statistics, incidents of drug use in the area. Because the national statistics about drug use based on visits to hospitals, needle exchanges, and things like that. So it's not based purely on criminal data, just based on other forms of data as well. And that left-hand side picture is a heat map showing where, based on that national level data, where people are likely to be doing drugs. Okay, so there's some kind of more hotspots, but there's a kind of a spread across the entire East Bay. They took this data as a way to generate, sort of essentially simulate real data to put into the Predpol algorithm and say, okay, if you saw data like this, where would your system start to converge on where to sort of do policing? And the system converged into that, which, as you can see, is a very, very sort of concentrated area, which has relatively little to do with the actual prevalence of use of drugs. And again, this is intuitive. If the system sees, oh, there's some crime happening here, but not anywhere else, it'll double down on its predictions for the next round and keep updating it appropriately. Right? So this is not, for anyone who knows machine learning, this is not too surprising. But the question is, can we sort of formalize what's going on here? So can you build a model where this would happen? And so you can start off by doing this. And so there's some work we did. We said, okay, let's try to build a formal model for how such a system might be working. These are systems that basically work on, they build an EM style sort of non-parametric model, and based on the idea of crime being like an earthquake. So a crime is like a shock, and it causes aftershocks in space and time. And so if you model a system like a system with shocks, you can, and look at the new data coming in, you can build a parametric, you can get the parameters of what the aftershock model would look like. So you can abstract out the key elements of your system, and in fact, this is basically what the system will use. It did not retain any information about the crime except the fact that the crime happened. This was their attempt to not be biased, in some sense, about the demographics and other things. And the goal, again, is to get sort of X% of policing with X% of crime. That's sort of an intuitive idea that you want. So it turns out the right formalism to think about these questions is what are called these Urn models. If you've ever come across things like Polya urns and other urns, they're this beautiful collection of models that capture stochastic processes. And in a very simple way, the way they work is you say, okay, I have an urn, I sample a ball from the urn at random, it has a couple of colors, and based on this replacement rule, I throw the ball back in, but I might throw more balls back in of different colors based on what I see. So in this case, I sample that ball from the urn, I look up the table, it says, okay, you should replace one more ball the same color, so I do that. And I sample, and the question in this case is what is the limiting fraction of this color in the urn? And why this is relevant for this problem is that you can think of, in the simplest case, two neighborhoods. Each neighborhood is one color. Visiting a neighborhood corresponds to sampling a ball that color, and observing a crime corresponds to adding a new ball that color. So once you set up the system, you can start asking questions like, well, knowing what we know about urn limiting sort of distributions, can we say something of what the policing model is going to do? And it turns out it's quite depressing. So for example, assuming that regions have the same crime rate, and you have this model, you can now say, based on this sample replacement table, what is the limiting fraction of the number of gray balls in the urn? So there's a very simple Polya urn. If you've ever seen Polya urns, you know what the answer to this question is. The answer is that if the crime rate's uniform, and it starts with a certain number of gray and black, the limiting probability is a uniform distribution, controlled by only the starting number of balls in the bin. It's not one or the other. It's not 50-50. It only depends on what the urn started with. It does not depend on what you actually observe. So the output, the resulting limiting behavior of the model is independent of the actual crime rate. It actually only depends on your initial belief. If you seeded the model with a biased belief about where crime was happening, that's what you'll get. And this comes directly from the results from Polya urns. You can say, well, okay, crime rates are never the same, they're different. And if you have different crime rates, you can say, well, maybe the model will converge to some kind of hybrid model to do things. In fact, even that doesn't happen. There's a beautiful theorem that basically says that if you have a generalized urn model and there are 4 parameters, solve this magic quadratic equation, and one of the roots of that equation will tell you what the limiting probability is. It's a really nice result. This is from this paper by Renland. And in the case we were looking at, you solve it. It basically says that if you have crime rates that are even slightly different, the limiting belief, the limiting probability of one color in the urn will be 1, the one that's slightly more. So if you have 2 neighborhoods with like 55% and 45% of the share of crime, and you run this predictive policing system on them, it will inevitably converge to putting all its weight on one anomaly. And in some sense, this should not be surprising if you've ever done a class in online learning or reinforcement learning. This is exactly why you have these systems. So there are two ways to think about this now. Now that you have such a system, how do you try to sort of alleviate the problems of such a model? One is a black box approach where you can say, look, I can't touch the system. The police have deployed this, but maybe I can modify the process by which data is put into the model in the first place. I can somehow censor some of my data so I don't take it so seriously. So there's a formal way to do this, which I won't get into here. Intuitively, it basically says, if I expect a region to have a lot of crime and I see crime there, I shouldn't be adding that to my model because it's not surprising. I should only add it with a tiny probability. And that allows you to sort of to balance out the probabilities in a way that makes sure you get what you want. But a more interesting approach, which in a different paper they wrote, is to model this as a formal reinforcement learning problem and see if you can get good regret bounds for such a reinforcement learning problem. And so this is something that we did. And in fact, there's been some nice follow-up work on this in recent months as well. So looking at the questions. So this is a problem of feedback that typically has not been considered very much, right? This idea that your decision-making system over time will create the data that is used to train the system the next time around. And it's something you have to consider if you're going to build such a system. You can't ignore the fact that your system is changing the world around you. But another form of feedback is a kind of game theoretic feedback. Right? So suppose you're designing a decision process and you want to make sure that people can't strategically play games to seek an advantage in your system. They can't change their attributes, they can't do something else. So some recent work on this has sort of looked at how can you build a system that's strategy proof, that can resist the attempts of individuals to modify their data to sort of get a good outcome from the system. And some of this is basically bad news that basically say that if you want to build a system that's both fair, but also resistant to strategic manipulation by users, you're actually going to end up with a system that's not fair in the process. And there are technical details about what this means in these specific cases. So there's, I think, more work to be done on particularly defining the games that are being played and what you can and cannot do. But there's some interesting early negative evidence here. And in the realm of feedback, there's even more. You can now think of a process as a pipeline. So it's not just that I have a process to get into college that I want to be fair. Well, it's the whole college to going to grad school maybe, or getting a job, or getting a promotion. We talk a lot about sort of bias and pipelines in tech in the US. The question is, where do you make interventions to make sure that you can get equitable decision making across a pipeline? Since most decision making systems are pipelines, this seems like a reasonable question to ask. And so first of all, you can ask questions like, well, if you can get a system that's fair here and that pipes into another decision and you make that fair, do these things compose? There's this bunch of work that says no, that these things do not compose for all your favorite definitions of fairness. So you cannot guarantee that the end-to-end system will be fair just because you guarantee the individual piece will be fair, except under certain very specific conditions. Yes? Oh, it's a little tricky. It requires sort of, yeah, I'm not sure I can give you an intuitive answer to this. So basically, you need to manipulate probabilities in a certain way to make this happen. Yeah, sorry, we can talk offline about this.
I guess maybe a more meta question is, are the examples toy examples, or can you kind of come up with a concrete situation where actually, ensuring that, not ensuring, but process-wise, really process-wise, fairness does not kind of generalize?
So I would say all the examples are toy, both the examples where you break composition and the examples where you can retrieve compositionality, they're all toy examples right now. So the conditions under which you can retrieve compositionality are strong, and the conditions under which you can break fairness are these toy examples. So they're all kind of, but the second sort of work here, so this idea of how to make intermediate interventions so as to achieve end-to-end fairness are interesting because they are looking at actual systems of this kind. And there are a mix of positive and negative results that basically say that, for example, if you want to look at how a university reveals grades of students in a way such that you have equitable outcomes for a hiring manager who's hiring students from the university, then if the university does release grades, then you'll have a problem. And if they don't release grades, then you won't have a problem, that you can actually build a fair system in that process. So I would say the answer is still, I'm not quite sure yet how to capture this. But I think this question is interesting because real systems do have this pipeline effect. And thinking about where to make interventions is a very good policy question that people are trying to ask right now. Yeah.
Short follow-up to that is that, okay, so let's say that now we agree that, my process is fair on each one of its components.
Mm-hmm.
Then it's following up on what we talked about earlier. Like, so what's, and and yet somehow a minority is being discriminated.
Right.
Right. So, in some from some kind of very narrow legal perspective, I could say, I've done all I could.
What can I do now, right?
Yeah, what do you want me to do now?
Right. So I think there are two ways to look at this. One is to look at the study of this question as a policy question. In other words, where should we invest our energies and efforts in doing interventions to make sure we have more equitable decision making across the pipeline? Where's the most effective place, right? Should we be doing more outreach at the high school level? Should we be doing more outreach at the college level? And intuitively, the earlier seems like the better, but maybe you can formalize some of these questions. The other way to ask the question is a legal question. Right, so you have a pipeline system, you have a whole decision-making process, you've built some auditing mechanisms into it, but now it has failed. Where is the problem? Can you identify where the problem comes from? So I think they're different, depending on who's asking, you might have different sub-questions that might be relevant here. So that's how I would think about these questions, yeah. But as you see, as we're getting to this, these questions are not purely technical, right? They are questions that are now beginning to entangle with larger questions of how we design policy, how we think about society, how we build legal frameworks, how we build other normative frameworks for achieving equitable decision making. And that brings me to my last sort of expansion, so the expansion to society. So one of the interesting sort of aspects of this area that I've been working in is that you very quickly start realizing you're bumping up against very deep sort of questions in philosophy and sociology and the law. And somehow reckoning with these questions is important because it's not enough for you to build a tiny piece of system that seems to do something well. Once you insert into a larger framework, a societal framework, weird unintended consequences happen that you have to account for, such as. So the first paper that I want to talk about here is a very nice paper that's about to be published in a few weeks. This is basically looking at the history of fairness and unfairness. And it turns out that, maybe not surprisingly, everything I told you in the first half of the talk has already been done before. In fact, 50 years ago, in the context of testing for looking at sort of standardized tests in schools. So when standardized tests were being introduced, people are very worried about racial bias in this, whether they were unfairly disadvantaging minority students because of the way the tests were constructed. And in order to articulate those concerns, they had to come up with definitions of fairness and unfairness and so on. So it's kind of uncanny if you read this paper how that whole discussion is parallel to the discussion I gave to you earlier. So I pretended that it was something that we all came up with in the last 10 years, but actually all of these discussions have been around much longer than that in almost exactly the same form, with exactly the same kind of complaints and arguments and impossibility results and so on. So I think, just as a matter of historical record, it's very interesting to look at both that literature and why it died away, and why people stopped looking at those questions and why they gave up. And I think one of the messages that the authors argue for is that, and this is a sort of subtle message, that we spend a lot of time defining fairness. We should spend much more time defining unfairness. Now, this is not sort of an NP versus co-NP kind of thing, although I think sometimes it is. But I think the point is that it is easier, in a social sense, to articulate when something is unfair than to articulate when something is fair. And some of the problems with the earlier work in this area, that people at some point, for no reason, shifted from thinking about unfairness to thinking about fairness, and then realized none of their methods were actually working very well. So this is something I'm still wrestling with myself. I've had long back and forth with the authors about this, trying to understand what this means. But I think it seems like it's one of those things where it's easy to measure where something is going wrong. It's much harder to certify that things are going right. But if you set up a series of processes to detect when things are going wrong, that might be a good step forward to sort of build systems that can at least raise alarm bells, without claiming that when there are no alarm bells, everything is fine. So that's one lesson that we sort of learned from this literature here. Another question that sort of brings, yeah. Yeah.
So early you had many definitions of fairness, but they were not necessarily compatible.
That's right, and they aren't.
Would the definition of unfairness be compatible?
I think you wouldn't even, in some sense, you wouldn't need to ask that question, because you could have different ways of being unfair, and it would be okay to have different approaches. I think maybe that's their point, that when you're saying something is fair, it seems like an absolute ideal, and therefore every definition of fairness should look the same. Whereas it's okay to be unfair in sort of different ways, and it's perfectly fine to have different notions of unfairness. And maybe that's a better, more productive way to think about this. So I forgot the Dostoevsky quote, right? Every happy family is happy the same. Every family is unhappy in a different way, or something. That's kind of thing. Yes. Is that how it goes? I'm not sure. Sorry?
All happy people or happy families are the same, but the unhappy person is unhappy.
Yes. So that's what I always think of when I think about this. So yes.
But also maybe it's an answer to one question. One of the things that will be evident here invariably need the emergence of another type control. You can't, there are no free lunches.
Right, right. And I think what that does is it then forces you to have the larger, harder ethical discussions about what is it you want in your system. So I mean, it's easy to come away from the stock thinking, okay, I'll just pick the most popular notion of fairness or unfairness and optimize my function. I think that misses the point. I think the point of having these different notions is that they capture different ideals of what we want with our decision making, and they are different, and they differ based on who we are and who we're working with, and that kind of hard discussion is something we have to have. But by having these as proxies for our ethical sort of positions, we can have that discussion in some way. But yeah, but it is something we have to think through a bit more carefully. Another thing that you have to deal with in dealing with the fact that at some level there are going to be people making decisions based on this is that people don't necessarily listen to what the algorithm is telling them or that this is going to do. So there's been some interesting work, again, in the realm of criminal justice, looking at, well, what happens if I give a judge a score for a person saying, well, this person is, has a risk score of 5 out of 6 of not showing up if you give them bail. What does the judge do then? Does the judge listen to it, or does the judge not listen? So there's a long-running study that Megan Stevenson sort of wrote about where this pretrial risk assessment system was rolled out in Kentucky, in one of the states in the US. And she wanted to look at whether judges were taking the recommendation of the system into account when making their decisions about whether to give someone bail or not. And some of this was quite depressing. Basically, first of all, there were changes initially. While there were changes in the amount of bail that was handed out, there was very little change on the decision of whether to release someone or not. So it wasn't as influential as they thought. And worse, over time, the judges reverted to their pre-risk assessment tool behavior. They just stopped paying attention to it altogether. So this is kind of a depressing story of what happens when we put in such a system that we believe is going to be fairer. It doesn't matter if the judge is not going to pay attention to it. And so one of the things I do on the side is I'm on the Research Advisory Council for New York City's failure to appear risk assessment tool. So New York City is building their own tool, and there's a bunch of us on a research council advising them on how they do this. And that's one thing that they're very concerned about. They've been building a tool, they've been going talking to judges, and if the tool, say, for example, recommends that more people should be released than they thought, the judge's like, I don't think that makes sense. I have all these 20 years of experience, and I don't think you're right. Whether the judge is right or wrong is irrelevant. The point is they have the power. And so when you build these systems, you have to take into account the fact that there is this other party out there that's looking at the output of this recommendation and is doing something with it that you may not expect. A simulated study, a Mechanical Turk study that's got published recently, sort of showed something similar, that if people were given sort of guidance from an algorithm on how to make recommendations, they still exhibited biased behavior with respect to minorities, even when they were given this guidance. And they still didn't do very well compared to the algorithm itself. So there are all kinds of issues here involving how we present this information to people who are going to make decisions and how they're going to take them and what's the best way to do this that is beyond the scope of what I know and what I can even talk about, but I think is relevant for whether we hope to actually make any difference with the kinds of tools we're building here. And that sort of brings me to another point, that when we sort of claim we are building a fairness-aware machine learning algorithm, we're not really doing that. We're building in one piece of a much larger system. It could be a pipeline of the kind I described to you, but it's a much more complex system, right? And so you kind of have to understand how that piece of technology is going to affect the system around it when you put it in. Otherwise, you will essentially solve the wrong problem. And so this is by way of sort of starting a punchline, sort of do a joke, like most jokes start. This is how this joke started. Well, actually, it didn't quite start that way. It started that way, and this sort of led to a paper that I just recently wrote with a bunch of colleagues, 2 sociologists and a lawyer and another computer scientist. And what we were looking at is something sort of a more fundamental problem with the way we've been articulating these questions, which I'll call the problem with abstraction. Right? And the problem is the following. So we are taught in computer science to abstract things. We are taught to always throw away the stuff that's not relevant, find the right level of abstraction, and then solve the problem at level of abstraction, and then take a solution and then apply it, right? And it turns out that very power, the thing that's sort of the most powerful aspect of our field in some sense, is also a problem when we deploy these systems in these larger human and tech mixed systems, these socio-technical systems. And in order to avoid making the problem worse when we build these fair decision-making systems, we have to understand what happens or what kind of traps we fall into when we put, when we build algorithms for them. So in particular, here are some of the traps. So one trap is, like I told you, this problem of failing to model the entire system over to which a criterion like fairness, which is fundamentally a social criterion, not a technical criterion, will be enforced. This was the issue of dealing with judges, right? So fair risk assessments provide guarantees on disparate impact, but if a judge doesn't pay attention, it doesn't really matter very much. We just talked about that right now. Another trap is what we call the modularity trap. It's sort of failing to understand how repurposing algorithmic solutions designed for one context won't really apply if you put them in a different context. So this has been some work that we've been doing on trying to understand how different beliefs about the world will change what fairness measure you use. But you've also seen this in the context of saying, if I build a classifier that can classify, that can do binary classification, I'll apply it to solve an MRI classification problem to decide who has Alzheimer's. I'll solve it, I'll use the same classifier to decide whether someone should be released on parole. It's a different problem, a different setting. The same system doesn't really work across both of these. The formalism trap is a bit harder because, as I said, the whole goal of what we do in computer science is to formalize and abstract and make mathematical things that are fuzzy. The argument here is that this itself is a problem because definitions of fairness, especially in the law, are often process-based rather than outcome-based. In other words, you specify a sequence of events, and as long as you follow the sequence of events, your system is fair or correct. And that's not how we do things in computer science. We define things in terms of outcomes. They also depend on the context, like I said, but they also depend, they're contested. In other words, different people argue about, you have to build a system that different people can argue about and come to some conclusion on, and by formalizing a system, you take away the fact that different stakeholders have different goals in how they want to build a system. Now, this is a bit fuzzy, but the basic problem is that if you have, for example, a system of defining fairness in criminal justice, the stakeholders are the judges, the lawyers, the prosecutors, the defense lawyers, the NGOs who work in the community, the politicians who are running the city. They all have different goals here. And your one measure that you formalize will not be able to capture all their different outputs. And so you're going to sort of privilege one group over another. Another problem is this, what we call the ripple effect trap, that once you build a system and deploy it, it starts having effects around. We've seen this already. We've also seen this, you may have heard about this problem here. Amazon built this automated hiring system, and they were running it, so testing it internally, and it was discriminating against women. They didn't realize why this was happening. It's because they were building it on past data on their hiring practices, which in fact was biased against women in the first place. So in one sense, this was a good outcome that the system allowed them to discover this inherent bias in their hiring practices. On the other hand, this fact, especially in hiring, where you build a system, you hire people based on the system is flawed, and you use the data on the people you hire to modify the system, this will not work, as we've seen. And finally, a trap that I like to call the Elon Musk trap. So building solutions for problems that don't need solutions. This is, again, this is the hardest of problems because as technologists, we want to believe that technology can solve problems. And sometimes the solution does not come from tech altogether. So that's a case where maybe we need to stand back and sort of question whether we should be building a system or not. Right? And that's kind of a hard thing to do. So there's a whole field of research, it turns out, that studies these questions. Yeah. Okay, there's a whole field of research that studies these questions called science and technology studies. And they sort of look at this problem of how you inject technology into society and understand the percolative effects of how society reacts to the introduction of technology and how the technology changes in response to societal pressures. And so it turns out if you bring in insights from this field, which is sort of a subfield of sociology in general, you might get better insights on how to avoid these kind of traps. So for example, in the cases I was describing to you, if you want to avoid the framing trap, you have to incorporate sort of human processes in this. So this paper that I mentioned to you, the Green and Chen paper, that looks at how people react to being given a recommendation from an algorithm. The fact that people react a certain way might tell you how to design the system, knowing that someone's going to look at the results of your system. Right? Again, I don't have a clear formula for how to do this, but depending on the circumstance, you have to keep that in mind, that there's going to be a human at the end of the pipeline making that decision. Avoiding the modularity trap, there's been a bunch of interesting work. So it's kind of fun that we wrote this paper, and then we went back and looked over the recent literature in fairness, and we're realizing that a lot of people are sort of from separate directions coming to the same conclusion about what needs to happen. So in particular, the idea of the modularity trap, if you recall, is this problem of taking a system and applying it somewhere where it's out of context, and you didn't realize it. So a lot of people are now looking at things like, can you come up with like a data sheet for a data set, where the data sheet tells you interesting factors, properties of the data set that will tell you when you can apply it in a different context or not, right? So the data set has this kind of biases, it has this kind of skews. So now if I'm going to apply it somewhere, I know what kind of specs it has. So this idea of data sheets is drawn from the idea of spec sheets for, let's say, a transistor or some kind of operating system, some kind of electronic part. People have proposed the same idea for models. Once you build a model and you want to sort of give the model to someone to use, you have to have sort of a sheet of information around it that tells you things like its false positive, false negative profile, how it was trained, what kind of data sets it works on, and so on. And so you have to carry that information about the data sets it was trained on along with the model. And other things about this, things called nutrition labels and information about different ranking schemes. There's a whole bunch of work now trying to say that once I build a model, I put some information around it to describe the context in which it works correctly. So that if you do apply it in a different context, you have at least some way of telling whether it's going to work well or not. Again, avoiding the formalism trap is tricky. The trick is to sort of make sure that you don't settle on one definition. You don't have this quest for the one true definition of fairness. You keep a bunch of definitions around, realizing that they tell you different things about the problem. And that's going to be important. It's what's called interpretive flexibility. And finally, dealing with ripple effects, like I mentioned, this issue of modeling feedback loops, modeling strategic classification. Again, there's a bunch of more work in this area, trying to understand how feedback in the system might affect how the system gets built. So that sort of brings me towards the end of my talk here. Just want to review some of the things I did tell you about. I talked about sort of this basic question of defining fairness and unfairness and fairness enhancing procedures. I've talked about how to understand the interaction between system and agents, understand the influence of inputs to black or gray box procedures, and also how to evaluate these interventions in a larger social context. A lot of things I didn't tell you about, which is also our active areas in the field, are articulating harms of representation. So for example, if you do Google search for a CEO image search, you'll, at least when I've done this and this in the US, you'll get, if you do an image search for CEO, you'll get a bunch of pictures of white old men. Now this is sort of a factual representation of the fact that the way CEOs look. This is also, in some sense, a strategic choice of a lot of these sort of the stock photo companies that are trying to make you buy stock photos and are sort of therefore doing SEO to make sure that the Google image search will pop up their database, which looks very conventional. At any rate, what you're getting from these kinds of search results are kind of representations that are skewed in some way. Now, I'm not trying to judge whether it's a bad answer or a good answer, but the point is that what you get from a filtered representation of the world is a certain different form of representation than maybe what you expect. And so Kate Crawford, in a very nice talk at NeurIPS last year, talked about this idea of harms of representation. What happens when your representations themselves, the core data used to build models, have skew in them? And there's been some other work on this as well. This is sort of a garbage in, garbage out problem. When your representations themselves are bad, your outputs are going to be bad. How do you articulate these harms, and how do you mitigate them, if you can? Tools to interpret and explain decisions is a huge area of research. I actually cannot touch on this at all. A, because I don't work on it, and B, because it's just way too long to talk about here. This idea of, can you explain the result of a decision-making system? Can you interpret the result of a decision-making system? We talked a little bit about it, but there's much more to talk about there. And again, a lot of this is fueled by work on the GDPR. Interactions between policy, technology, and the law. Like I said, some of these things are sort of impedance mismatches between how computer science designs solutions to problems and how the law expects solutions to look like. And how we do that, again, this depends on context. In the US has a different context, Europe has a different context, different countries in Asia have a different context. And how you do that really is going to be very specific to your local context. And so how to do that is unclear at this point. And again, another big issue that I know Reza and I have talked about a bit is this whole tension between privacy and the desire of fairness, right? If you want, so for example, if you want to make sure your data is private, you might conceal certain forms of data, or you might prevent systems from using certain aspects of your data. But if you do that, the system may not be able to get enough information to make sure it makes a fair decision. And so the question is, is there a tension? Is there a way to reconcile them? How do we think about this? These are all sort of open questions that people are slowly beginning to explore. As you can see, these questions come from many different disciplines. I think that's what's interesting about it. In some sense, I feel like this is a new area. It's an area that draws on ideas from computer science, of course, because we're building the tools here. But it also draws on ideas from economics, from sociology, political science, law, and many others. And they all sort of come together in this mishmash, which we're still trying to figure out and make sense out of. So it's both exciting and confusing all at the same time. And with that, I will conclude. Thank you all for listening. And it was my job.